Hi, this is the Renegade Mathematician. Thanks for tuning in again. And in this video we're going to continue our discussion of the properties of determinants, and we're going to look at one fundamental property which says that you can take a determinant and turn it into a bunch of other determinants. But before we do that, I do want to note that we will now refer to determinants wherever convenient without explicitly referencing the two-dimensional array of numbers or matrix that we are taking the determinant of. Observe that Shilov has been doing this the entire time and has yet to mention such a thing as a matrix. So, keep that in mind. So, let's start it off with a definition. We define a linear combination of numbers, x sub 1, x sub 2, x sub 3, all the way to x sub n, to be any sum, c sub 1, x sub 1, plus c sub 2, x sub 2, plus blah 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 blah, c sub n, x sub n, where c sub 1, c sub 2, all the way to c sub n are also numbers. And this is kind of a simplistic definition, but it's an important concept, and we're going to be, we'll talk about it more in the future. It's going to be something that, in the subject, you're going to be dealing with constantly. So, property 1.44, referred to in the book as the linearity property of determinants, says the following. Let D be some determinant, the entries of whose jth column are linear combinations of the form a sub I j is equal to lambda x sub I plus mu y sub I for all I in the set 1 through n. Okay, so everything in the jth column is a linear combination that looks like that. Then we may write the determinant D as the linear combination of determinants. D is equal to lambda d sub 1 plus mu d sub 2, where d sub 1 and d sub 2 have the same entries as D, except in the jth column. The jth column of D1 contains the entries x sub I, and the jth column of D2 contains the entries y sub I. Okay, and this is what I'm talking about for you visual people out there. Notice that in the leftmost determinant, I'm not saying matrix, it's a determinant. The straight bars tell you it's a determinant. The jth column, right, and the note in the determinant just to the right of that, we've replaced all the entries in the jth column with linear combinations of x and y. And the subscripts change as the row changes. So in the first row it's x1 and y1, and in the nth row it's x sub n and y sub n. But that is equal to a linear combination of determinants with where one of the determinants has just the x's and the other one has just the y's, and they we've kind of factored out, so to speak, the lambda and the mu. Okay, here's the proof. So D is equal to a determinant, and that's just the definition of determinants, right? That's what a determinant is. Get used to it. But that is equal to the same thing, but instead of what we've done is we've substituted for a sub alpha j, because that entry is in the jth column, and everything in the jth column is a linear combination of x's and y's. We can write that as lambda times x sub alpha of j plus mu times y sub alpha of j. Right? Okay. And also note that because we have that linear combination, what that is that's a sum in the midst of a product of entries in the matrix. And so we can use the distributive property. So by the distributive property, right, we have broken it up into a sum of sums, right? We have a sigma that's a sum, and then we've broken it up into the sum of two more things inside that sum. So we're summing sums. Anyway, here we go. But note that since the sum of sums is the sum of sums, it's hilarious, we could just write that with another sigma. No biggie. Yeah. And to follow that up, we can also factor then out the lambda and the mu, because lambda is common to every term in the sum, in the leftmost sum, and mu is common to every term in the rightmost sum, we can just factor those out, and that's, again, by distributivity. Okay? But then what we have is lambda times d1 plus mu times d2 by definition of d1 and d2, right? Those sums are just determinants, namely d1 and d2. QED, we proved it. How about that? And ta-da. So once the following notation is established, property 1.44 can easily be extended to columns consisting of larger linear combinations. Really, the sky's the limit. So given determinant D, define D sub j of x sub I to be the determinant D with entries in the jth column, right? That's what the subscript j denotes, the column we're replacing. So entries in the jth column replaced by the numbers x sub I for I in the set 1 through n. Okay? Then property 1.44 can be reformulated. D sub j of a times x sub I plus b times y sub I plus c times z sub I is equal to a linear combination of determinants, right? It's equal to a times d sub j of x sub I plus b times d sub j of y sub I plus c times d sub j of z sub I. We can break it up in that manner. So we start with a determinant whose jth column is a linear combination. It consists of linear combinations. And then what we can do is we can break that up into, instead of a column consisting of linear combinations, we have a linear combination of determinants. That's what we get. And for you visual people, here's what I'm talking about. Notice the jth column is linear combinations, and I've split it up into a linear combination of determinants. And the viewer should pause this video and attempt to prove this extension of property 1.44 using our proof of property 1.44 as a reference. You can literally just use it like a roadmap and prove this extension. Heck, it's easy. Do it. Anyway, that's the end of the video. Hope you enjoyed it. Join me next time for more properties of determinants. Bye.